Now let's come to the awarded best paper. It's called Mosaic, which is going to be presented by Kai Shi, who is the principal research in the Future AI Infrastructure Group at Microsoft Research Cambridge. Well, he explores solutions to the challenges of optical networking for next generation data center. This is your first SIGCOMM' paper, right? Yeah, he told me that. Congratulations. Now it's your time.
Thank you very much for the kind introduction. This is a joint collaboration between Microsoft Research and many of our colleagues from the product team in Microsoft Azure. Today, I would like to share with you the experience or the journey that we've been taken of using a wide and slow architecture combined with MicroLEDs to break the trade-off between copper and optics. This has been a fundamental trade-off over the past decades. It's really forcing designers to make hard choices. So what is it? Let's take the NVIDIA GPU networking as an example. For high bandwidth applications like the NVLinks, we have to use in copper because it's a very power efficient, low cost, and it's a passive components, so it's very reliable. But the transmission distance is really limited to a couple of meters, so it can only cover a range of 72 GPUs. In order to scale out to tens or hundreds of thousands of GPUs, we have to use in optics. Optics, on the other hand, originally designed for long-haul transmissions, which can support tens or even hundreds of kilometers. It was great for the transmission distance, but it's using very power-hungry and expensive components. More importantly, because it's using lasers, it's very sensitive to the operation condition like temperature, which makes them orders of magnitude worse in terms of reliability. So we have to sacrifice the bandwidth. So as you can see now, there's already a 10x oversubscription between the two bandwidth domains. The consequence of this is really severe. In order to maximize the high bandwidth domain provided by copper, what people intend to do is to really put in as many GPUs as possible. That's really pushing the complexity to the power density of the rack and also the cooling systems. Just to give you a concrete example, today's NV72 rack is already consuming 120 kilowatts. That's 60 washing machines being crammed into an area slightly bigger than my size. And that number is getting even crazier for the next generation, going to be over 0.5 megawatts. But fundamentally, what is really limiting here is the size of the scale-up network. We're also facing the same situation in the scalability of the memory as well. Because now the bandwidth that's needed between the GPU and the memory, the copper traces can only cover a few millimeters. So the high bandwidth memory, the HBMs, has to be allocated really on the edges of the GPU, sometimes we call them shoreline. So you can see here, it's very challenging to scale the capacity of the HBMs because we are running out of real estates. And the only way the industry is trying to do is really to increase the number of layers in the DRAMs inside the high bandwidth memory. That's extremely challenging. Or we have to significantly increase the size of the package, which is also very complex and power hungry. By combining these two, it's really making the scaling of both memory capacity and the networking bandwidth being lagging behind the computing power provided by the GPUs over the past few generations. So our AI workload, especially the inference workload, is really become I/O bounded, that we cannot fully utilize the power provided by the GPUs. So in order to close this gap and break the trade-off, we, in close collaboration with our product team partners, brought Mosaic, which is basically a combination of wide and slow architecture together with MicroLEDs. And we believe this technology can provide a significant reduction of power using very low-cost components, and also can be as reliable as copper cables. And you can see more significantly, it also extended the reach from a couple of meters up to 15 meters. Obviously, this is not a free lunch. We're not using lasers anymore. We cannot go beyond hundreds of meters, but 50 meters is already large enough to cover a whole row of racks containing thousands of GPUs. So that's what we believe this technology can really help us to solve some of the pain points that we are facing today in the infrastructures. But it can also open up a lot of new opportunities for the future AI infrastructure. Before I get there, first let me show you how the technology works. It is quite important for you to first understand what's the fundamental limits of today's technology. So if we will open one of these boxes here, sometimes they're called a module. you will see they are adapting a narrow and fast approach, which means that it's only using a small number of channels, but really driving them at extremely high speed, hundreds of gigabits per second. So what's the impact of that? For the copper cable, the loss of the copper increased significantly when we go into higher and higher speed. So you can see the coverage provided by the copper cable shrinks over generations. Now it's a couple of meters, and the next generation can be even smaller. Optics, although it has no issue with the transmission distance, but because the use of these power-hungry, expensive components, both on the optic side and on the electronic side, they are really pushing the power consumption of these cables over generations to be higher and higher. So currently, these tiny little boxes are already consuming 20 watts, and the next generation, that's going to be 50 watts. So this is really triggering us to think, if we continue with the same architecture, it will be extremely hard for us to scale. That's why we go to the opposite direction, adopting a wide and slow architecture. So to achieve the same 800 gigabit per second, instead of using 8 channels, now we can use actually 400 channels and lower the rate of each channel to only 2 gigabit per second. So now immediately we can use not expensive, complex electronics. Actually, we can use very simple architecture designs, can be power efficient. But if we're only using 400 lasers, from cost, power, and reliability point of view, it's not going to be feasible. And this is where MicroLED becomes a great candidate. So MicroLED itself, originally designed for display purposes, is the same as any of the LEDs we use for lighting, but the size is on the order of microns. It's been widely used in some of, for example, the smart watches, also for the head-mounted devices for the AR and the VR applications. So it was born naturally to be able to integrate with millions of pixels with a smaller size. So we can easily, for example, get a 400 microLED array on the size of 1 millimeters. And also now we're operating invisible, so we can use very standard CMOS sensors, similar to the ones that are on the back of your mobile cameras as our receiver. But if we're now going to simply just using the same 400 fibers that are used as in today's transceiver, the cost was still going to blow up. And that's why we identified this imaging fiber with a very simple process. It can contain thousands of cores to support hundreds of channels. It was originally designed for medical purposes, for endoscopy, but now we're using them for communication. Combining all these three together, so we have a solution now can provide power efficient, cost effective to building up our links. It also opens up the opportunity for us to have redundant channels. Let's put aside the MicroLED itself. The structure is much simpler, the fabrication is much simpler than lasers. It's already quite reliable, as it doesn't have dependencies on the operating conditions. But with these redundant channels, it can further help us to increase the reliability. As you probably already noticed, the diagram we are using here, that our technology is compatible with the same form factor as being used today. So it can be a very simple plug-in replacement without any modifications either on the switches or on the NICs. And also, we are not terminating the connection, we are not inspecting the packets, so it can be agnostic to all the protocols. It can be used to support Ethernet, NVLinks, or CXL. So I may make this sound quite simple, but actually, since we fundamentally move away from laser-based systems to microLEDs, there are a lot of challenges. For example, the microLEDs were originally designed to be flashed at a rate of a few hundred times per second. Can we really turn them on and off at billions times per second? But this is really an innovation that we have to do across the whole stack to solve some of the challenges, not just focus on the microLEDs. And that's why we also have a team that with expertise spans across the whole stack. For example, we need to design efficient optics to couple light into the fiber. We need digital designs to be able to understand how we can implement this wide and slow architecture. And we also need to package and assemble them eventually into a module form factor. But more recently, the team has also started to think, because now we are not using this, we are using our imaging fiber. Can we be compatible with, for example, connectorized applications like shuffle cables or optical circuit switch? So due to the time limitation today, most of the information, the details you can find in the paper. I'm just going to give you 2 examples. First is to give you a flavor how we innovate some of the challenges using optics. And the other one is really that now we move away from this narrow and fast architecture to the wide and slow. What are the opportunities it brings to us? I know many of you don't have the optics background. Just bear with me a few seconds, a few slides to show you some of the cool stuff we do on the micro-optics side. So the microLED itself is the same as lightning, so the light goes everywhere, plus or minus 90 degrees in the whole sphere. It's great for lighting, but it's not so great if we want to confine them into a fiber to transmit information. So what conventionally people intend to do in display is using a micro-lens arrays called MLAs. As you can see from simulation, it confines most of the beams, but there's still a lot of beams going to a relatively large angle. It not only reduces the efficiency, but also can cause a lot of interference to the adjacent channels. So that's what we have been innovating in-house to design or exploring different type of micro-lens surfaces. This one is called a total internal reflection lens. As you can see from simulation, it can significantly improve the directionality of the beam. But our innovation or design doesn't really stop by the simulation. We work closely with suppliers. As you can see on the imaging here, it's actually a real TIR lenses being printed on the micro-LEDs on the size of a human hair. We're also working closely with the vendors to see how we can push this technology to mass production. So now let's have a look at the opportunities. If we think it again, this is really the first time we realize a parallel optical bus. So the parallel bus architecture has been very, very powerful, being widely used in electrical domains. For example, in the die-to-die connectivities between GPUs to GPUs, between GPUs to the high bandwidth memories. It can provide a lot of benefits that now we can apply them on the optics. And one of the key benefits is really that it allows us to over-provision channels at a minimum overhead. We can use these redundant channels to send in control information where the transmitter and the receiver can be exchanging information like the clock. It can help us to further reduce the power consumption. But what I really want to focus today is how we can use these redundant channels to help us to improve the yield as well as the reliability. If you think that we can basically use these redundant channels to tolerate any failures, whether that's happening at the fabrication stage, so we don't need 100% yield, or during runtime. Imagine there if it's the one channel failed, with a very simple error correction code, ECC, we can correct that error without even the application layer noticed. What is more powerful of the ECC is that it also tells us which channel failed, so we can hot swap it at runtime with another redundant channel. So we did some analysis in terms of the failures of this technology. So in industry, people intend to using FIT, failure in time, as the metric. I plot them on the y-axis in log scale. And this is where the optic-based transceivers and the copper-based links stands today. As I mentioned earlier, the coppers are orders of magnitude better in terms of reliability. So if we just very conservatively assume the fit rate of micro-LED is 1, even though when we talk with the display manufacturers, they say this number can be further reduced. If we don't have any redundancies, we will be operating the same level as optics-based links. But with a small introduction of a small percentage of redundancy, as you can see, we can significantly bring down the fit rate. Actually now, orders of magnitude and in the same level as copper cable. It has been a long journey, but we really believe this is the technology that can bring these key characteristics: low cost, low power, highly reliable, extended reach to copper, and also be compatible with today's infrastructure. But this can be a really big win to help us to solve some of the pain points we are facing today. But what we are more excited to bring this to this community is really to encourage people to think, what are the new opportunities this technology can bring to? For example, on the networking side, memory, as well as compute. Just to give you an example, since now we are extending the scale-up network reach, we are not forced to use these high-density racks designs as we're using today. So we can flexibly share the resources across a much bigger scope. On the memory side, also because we are using provide the high bandwidth, we can actually offload the high bandwidth memories from the package, so we are not limited by the real estates to help us to scale the capacity of the memory, and also opens up opportunities for us to using other type of memories. But fundamentally, the I/O bandwidth of an accelerator is still limited by the shorelines or the I/O pins around the edges. If we can directly put the micro-LEDs on top of the accelerators, I understand there's still a lot of challenges that need to be solved in the packaging world, but that can allow us to fully exploit in the whole area, not just the shorelines of the accelerator, potentially unlock petabit per second of bandwidth. So you can see there's already quite a lot of interesting opportunities. We are really keen to be here to engage with all of you to see what we can fully leverage the capabilities provided by this technology. Actually, we have a mini demo for all of you at our booths. If you are interested, please drop by for any further discussions. Thank you very much.
Thank you. Very nice talk, very inspiring talk. So questions?
Thanks so much for the talk. I have actually a little bit more detailed question. So in your paper, you're focusing on 20 to 30 meter links, and you basically, can you hear? Yeah, okay. So in your paper, you basically focus on 20 to 30 meter links, right? And you focus on chromatic dispersion as the main culprit. Most of the published LEDs, they focus on shorter links due to modal dispersion. Can you comment on how the modal and chromatic dispersion comparing your links? And if you did something special other than obviously the lens to combat the modal dispersion and the EQ used, the equalization?
Yeah, it's a great question, actually. Both dispersions are important to us. So for example, as you know, that the MicroLEDs, even though we say it's a single color, it's actually many, many shades of different colors. So different colors will be propagating at different speed. That's limiting on the chromatic dispersion. And also because the MicroLED, as I said, the light beams goes at a wider angle, so different angles will be also propagating at different speed, which is also kind of causing the modal dispersion. So for us, actually, especially for the long transmission distance that we are targeting at, both are extremely important for us. We have to tackle both.
Okay, so in your paper, you only mentioned chromatic, so you are actually seeing both dispersions dominate. And any special EQs you used? Equalization? Equalization? Equalization?
No, as I said, because the speed or the rate that we are running at is really, really low. So any standard equalization techniques we use in the electric domain can be implemented here. And then it's quite efficient to be able to implement them at such a low rate in general.
If I may, one more question on the fiber. Can you comment on the material NA and fill factor for the imaging fiber? Sorry,
the material and?
NA, the optical.
That's been the specific questions, but I can say that, again, the fiber, for us, the important part is that we need a low-cost fiber that will be able to support hundreds of channels. We are open to many different type of technologies.
I'll come find you. Thank you.
Thank you.
Questions?
Hi, thank you. That was very interesting. So simple question. The highest speed SerDes that you have today are 200 gigabits per second. And if I wanted to replace that with one of these micro-LED arrays, how many LEDs would I require?
So you are saying how to replace the SerDes with micro-LEDs?
How many? How many would I require to get the same bandwidth?
Yeah,
I'm trying to do a calculation based on the beachfront to the area.
Yeah, so as you see that, for example, in the 800 gig, we were using 400 channels, each of which are running at 2 gig. For the next generation, obviously there are different ways to, for example, further scale the speed. One way you can think is probably we can increase the line rate for each micro-LED to run a bit faster, and the other way to introduce in more channels. So I think the combination of these two will allow us to really scale to the 400 gig per lane generation.
Okay, and so then projecting forward, when do you see, let's say, a chip with, let's say, a 600 millimeter square area, and I'm able to have a flat array on top that completely covers the top of it, having the same bandwidth as what you would get from the beachfront?
So you were thinking how to integrate them on top of the accelerators, or?
So there's, okay, let me step back. The essential problem today is how do you get the maximum I/O out of a chip? Because you are bounded by the beachfront of the chip, right? And so if you're trying to not be bounded by the beachfront, but you want to have the area on top so that you scale by the square of the size of the chip, not by linear dimensions, then at some point the two curves are going to intersect where this becomes more efficient than trying to use the beachfront with long and narrow channels as you described. So I'm trying to see if I can project ahead and would like to get your best guess on that.
Yeah, it's going to be hard to predict because there's still a lot of challenges that need to be solved on the packaging side. For example, the thermal issues and all these kind of things. But that's definitely one of the direction to go because for us, it's, by nature, it's a 2D array. So it's quite easy to be able to fully utilize an area rather than just a shoreline. Even for the current generation, potentially we also can use in leverage the areas, so we are not bounded by as you said, the shoreline. We can also fully exploit in the areas beside the accelerators. But to your point, fundamentally, we do want to, well, it will be great to be able to see them being integrated. But again, the packagings, the whole stack needs to be fully optimized coherently.
Okay. Thank you.
Thank you.
Nick, just raise hand for the last question. Yeah.
I loved your talk. Super, really exciting. So I love the fact this last intriguing idea of moving away from the linear constraint of shoreline to aerial density. I think that's super exciting. But I have a different question, and this is about what do you think the consequences? Or what are you thinking in terms of the optical switch design? Because now it's actually got to switch a whole bundle instead. Or do you think that the lower power means you actually don't need an optical switch, you would actually convert back to the electronic domain?
It's great insight. I would say it can be both. Depends on the final power or picojoule per bit data of the end-to-end system. We actually have developed a couple of technologies to make this compatible with optical circuit switch at a relatively high radix as well. And on the other hand, there could be another designs if, as you said, the efficiency of the link transmitting data has become so low that we may not need it. So yeah, I would say both of your insights are something that we are looking at.
All right, let's thank the speaker for the great talk.